Hello. So, this is the next lecture on flexural or bending vibration of beam. Here we will continue doing what we were talking about in the last lecture. So, in this lecture, the first example that I will be solving is that of a free beam. So, we will try to find out the natural frequency and mode shape of a free beam. We have done similar problem for a simply supported beam and a fixed free beam. This example of a free beam has been carefully chosen to show the existence of a rigid body mode and therefore, the existence of a possible zero natural frequency which denotes the rigid body mode of a free beam. So, if we have a free beam undergoing flexural vibration, then there would be one rigid mode, that is the beam would be free to move in this direction. So, the beam will be free to move in this direction since there is no constraint in this direction, and because of this rigid body mode there would be a natural frequency which will be equal to 0. So, let us start with the generic solution of the mode shape of a beam, and then we will impose the boundary condition. So, this is the generic solution of the mode shape of a beam. Now, let us impose the boundary conditions for a free beam. So, the boundary condition is that at x equal to 0, so let this be x equal to 0 and let this be x equal to L, then at x equal to 0, the moment which can actually be written as E I into del 2 y by del x square is going to be 0, and the shear force Q, which is E I del 3 y by del x cube, would be a minus, that is equal to 0. So, if we follow the same process that we did for the previous example, this will lead to phi double dash 0 equals to 0, and this will lead to phi triple dash 0 equals to 0. Now, if I try to write phi double dash x, that is going to be minus beta square C 1 and phi triple dash x is going to be Therefore, I can write phi double dash 0 to be minus C2 plus C4 equals to 0 and phi triple dash 0 to be minus C1 plus C3 equals to 0. So, now from this 2 I get C4 is equal to C2 and C3 is equal to C1. So, if I write the simplified version of phi x, then this is going to be C1 this is going to be the simplified version of the mode shape P x. Now, let us impose the other two boundary conditions. So, what are the other two boundary conditions? At x equal to L, we have similar boundary condition, that moment which is E I, because it is a free moment, free end, and no externally applied moment is being given there, I can say this is equal to 0, which is going to imply that phi double dash L is equal to 0, and we can also say that shear force, which is minus E I, which is going to imply phi triple dash L is equal to 0. Now, what does phi double dash L denote? It is going to denote C1 minus sin beta L plus sin h beta L plus C2 minus cos beta. And that is equal to 0. So, I have skipped certain steps in between, but it is very straightforward, and one could follow that from this expression of phi x, phi double dash L is going to be this, and similarly phi triple dash L is going to be C1 minus cos beta L plus So, these are the two sets of equation that I get. So, using the similar logic that we have used earlier, in order to C1 and C2 to be non-linear, is to be non-trivial. So, let me first write this above equation in a matrix form. So, I will have minus So, using the same method that we have used earlier, saying that in order to C 1 and C 2 to be non-trivial or 0 solution, the determinant of this matrix should be equal to 0, or I can say that the determinant of this matrix has to be equal to 0. So, if I want to find out the determinant of this matrix, so I can say that so this leads to that is equal to 0. So, this if you simplify further, so minus sin square beta L and minus cos square beta L is equal to minus 1, sin h square beta L minus cos h square beta L is again minus 1. So, I have minus 2 minus plus 2 cos beta L cos h beta L is equal to 0. So, that implies cos beta L into cos h beta L is equal to 1. So, this equation similar to the last example can be solved numerically to obtain the solution for beta L. If you solve it, you will see the solution for beta L is 0 and then 4.73 and then 7.853 and so on. Now, we see beta L equals to 0 is a feasible solution of the system. So, which in turn is going to give me beta equals to 0. We can see from the expression for phi x that even if beta is equal to 0 in the expression of phi x, the value of phi x does not become non-trivial, or it does not become trivial, or it does not become 0. So, therefore, beta equals to 0 is an acceptable mathematical solution of the problem. This also is in congruence with what is observed physically, because this denotes a rigid body mode and a free beam has a rigid body mode, and this mathematical solution confirms the presence of rigid body mode in the free beam. So, now similar to the previous example, once beta L is derived, we can obtain the values of omega, omega 1, omega 2 and so on, infinite solutions of omega n corresponding to each numerical solution of beta L. And once omega or beta is obtained, we can find out the mode shape phi x, we can find out the solution for C 1 and C 2, and thereby find out the solution for the mode shape numerically. This might not be possible analytically, it might become tedious analytically. So, we have to solve it numerically and get hold of phi 1, phi 2 and so on phi n. So, a small code, writing a small code will actually help us to get the values for omega 1, omega 2 as well as phi 1 and phi 2. So, with this we are done with examples on finding out the natural frequency and mode shape of an Euler-Bernoulli beam with different boundary conditions. So, next we are going to move into the orthogonality of mode shape. So, we have been discussing that the mode shapes obtained for a continuous system, be it a bar under longitudinal vibration or a beam under flexural vibration or even a torsional bar or any other member, the mode shapes are orthogonal to each other, and the expression for orthogonality is actually given as 0 to L phi r x m x into phi s x dx is equal to 0 for all r not equal to s. So, this we have been discussing through examples in several form in the last few lectures. So, we have also derived this condition for the axial vibration in a rod. So, our next job or next topic is to derive this condition for an Euler-Bernoulli beam. So, let me first write down the equation of motion of an Euler-Bernoulli beam under normal mode of vibration. So, under rth normal mode, the equation of motion can be written as let me call this as equation 1. Similarly, under sth mode of under sth normal mode, so, please note that in the derivation that we are doing to prove the orthogonality of mode shapes, we are not assuming that the beam is having a uniform cross section or uniform distribution of mass and Young's modulus. We are keeping it generic, considering any possible variation of EI and M, so as to prove that this orthogonality holds for any configuration of the beam, does not need to be only uniform cross section beam. Now, what I do is that multiply both sides So, I take equation 1 and multiply both sides by phi s x and then integrate. So, if I do that, this is what I am going to get. Now, what I do is that I do integration by parts of the left hand side. If I do so, this is what I am going to get. So, now let us look into this boundary conditions. So, this boundary condition, if the boundary condition, so what are the conventional boundary conditions of an Euler Bernoulli beam? It is either simply supported, it is free, or it is fixed. Now, let us look into this boundary condition. If the beam is fixed in either x equal to 0 or x equal to L, then phi s is equal to 0. Therefore, this whole thing goes to 0 if it is fixed. Now, let us see simply supported. If it is simply supported, then also phi s x is equal to 0. Therefore, this whole thing goes to 0 if it is simply supported. If the boundary condition is free, then this part denotes the shear force, which is equal to 0. Therefore, even for free case, this part is equal to 0. So, this part is equal to 0 for all boundary conditions, that is simply supported, fixed, or free. So, this part is equal to 0. So, now if we simplify this, and therefore, my integral equation becomes minus Now, again let us integrate this part by parts. So, if I do that, then I have So, this is for 0 to L. Now, let us look into this boundary condition. So, this boundary condition is also 0 whether it is free, it is simply supported or fixed. So, if it is fixed, this part which is the slope is equal to 0. So, this whole thing goes to 0. If it is free, then this part which denotes the moment is equal to 0. And also if it is simply supported, this part which denotes the moment is equal to 0. So, this whole boundary condition goes to 0 for all boundary conditions. So, therefore, we are left with a very simple equation of 0 to L d2 phi s this is what we get. Let me call this as equation 3. So, if we repeat the same process, but we start with the equation under Sth normal mode, pre-multiply it with phi r x and then integrate and follow this integration by parts and apply the boundary condition, we are going to get another equation which is going to look like this. Now, if we subtract equation 4 from equation 3, my LHS goes equal to 0 and I am left with omega r square minus omega s square into 0 to L equal to 0. Now, since r is not equal to s, so let me clear this and write. So, the equation that we have is omega r square minus omega s square. So, in this equation that we have, r is not equal to s. Therefore, omega r square, which is the natural frequency of the rth mode, is not equal to omega s square. So, this part cannot be equal to 0. So, since this part is not equal to 0, this implies that 0 to L phi s x m x phi r x dx is equal to 0. So, this is my orthogonality condition for the mode shape. So, this is one part of the orthogonality expression. We have another expression. So, if this is equal to 0, then from either equation 3 or equation 4, we get another expression which is 0 to L d 2 phi s by dx square. Right. So, this is another expression that we get from either equation 3 or 4, provided this, since this is equal to 0. So, this is another expression for orthogonality. This is also orthogonality condition for mode shapes, right. So, these two orthogonality conditions will be very useful when we perform the modal analysis of a continuous system. So, in a similar way that we did modal analysis for a multi-degree of freedom system. So, in the next lecture, we will talk about how to do modal analysis of a continuous system and thereby solve the system to obtain the response. So, with this we end this lecture. Thank you.